Hi everyone. In this video we're going to keep talking about normal distributions, but this time we're going to actually talk about how normal distributions in statistics sometimes arise out of nowhere. And this is actually one of the most powerful aspects of the entire subject, and it's going to open the door for a lot of inferential statistics that we're going to be doing in the final unit of this class. So we're going to learn about this through the concept of sampling distributions. And in particular, our focus is going to be on a distribution of sample means. And I call the distribution of sample means the X-bar distribution. And so what I'd like to do to start this video is just explain to you how we can generate or theoretically create a distribution of sample means, this X-bar distribution. So if you look at the applet at the left of the page here, at the top, we have a population. So this black blob that you see at the top is actually our population. And if you look at the bottom of that black rectangle, you've got numbers 0 through 32. I like to think of this population as being 33 numbered marbles. So the marbles are numbered 0, 1, 2, 3, all the way up to 32. And these marbles are sitting in a bag, and I envision an experiment where maybe you're reaching into the bag, you're blindfolded, and you're pulling out a marble. And so every marble has an equally likely chance of being chosen. I think every marble would have, well, I guess if you have 33 numbers, each marble would have about a 3% chance, a 1 out of 33 chance of being chosen. And that's how you can justify this is actually a horizontal line going across the top of that population. We call this a uniform distribution. And I'm starting with this because I want to show you that even when our original population is something like a uniform population, a normal-like distribution can still arise through a process of sampling. And so to generate a distribution of sample means, this is theoretically what we would do. We would say, okay, let's take a sample from the original population, and we're going to take a sample of size 5. You can see it says on the bottom right of the applet that our sample size is 5. So we're going to sample 5 marbles with replacement, and then you're going to see those 5 marbles, when I click on animated sample, you're going to see those 5 marbles pop up in this middle of the page. And then on the bottom, where it says distribution of sample mean n equals 5, we are going to actually just plot the average of the 5 marbles that we have in the middle of the page. So let's get started. So animated sample. So the 5 marbles that were randomly chosen from the population are these 5 in the middle. And when I take the average of those, I end up with something, looks like it's about 21 or so. And I can click on animated sample, do this again, and I get 5 new marbles. I take the mean of those 5 new marbles, plot that second sample mean on the bottom. But to get a true distribution of sample means, I need more than just 2 sample means. I want thousands and thousands and thousands. So if we click on 10,000 samples, we're actually going to be able to simulate this process 10,000 times. So click on 10,000. And the result is pretty interesting. I mean, this looks very much like a normal distribution. It's not exactly a normal distribution, but it's very close. And we're actually trending towards getting a normal distribution. And I'll talk about why I'm using the word trending and what we can modify to converge to a true normal distribution with this distribution of sample means. But still, we see that it's very normal-like. And this distribution of sample means also has certain properties in relation to the original population that are worth noting. And so I'm going to put those things down right now. I'm going to say the mean of the distribution of sample means. I'm going to compare that to the mean of the original population. And if you look at the picture of the distribution of sample means on the bottom, and you look at the mean of on the left of that picture, it's 15.97. The mean of the population was 16. So we're already seeing, even with just 10,002 sample means plotted, that the mean of the distribution of sample means, it's almost right on with the mean of the population. And in fact, I think we can state that the mean of that X-bar distribution, the mean of the distribution of sample means, is in fact the same as the mean of the original population. As we do more samples, you would see those means align a little bit closer. And so you can see after 70,000 samples, I've got a mean now of 15.99. So to arrive at a true distribution of sample means, you really need to simulate this an infinite number of times. Another idea is there is much less variation in the distribution of sample means than there is in the original population. You can see that there's greater spread in the original population, and if you look over at the left, the variance in the original population is 90, meaning the standard deviation is the square root of 90, or a number between 9 and 10. And the standard deviation in the distribution of sample means on the bottom is 4.25. There's actually a relationship between the standard deviation in the distribution of sample means and the standard deviation in the original population, and it's this. The standard deviation in the distribution of sample means is the standard deviation in the original population divided by the square root of the sample size. So right now, I just want you to observe this process and know that if you take a sample and you take the mean of that sample and you plot that mean over and over and over again, eventually you can arrive at a distribution of sample means, and we can see that that distribution is normal-like with these properties of the mean of that distribution being the same as the mean of the original population, and the standard deviation in that distribution being the standard deviation in the original population divided by the square root of the sample size. Now take a look at, we're going to do the very same type of thing, but take a look at the difference between a distribution of sample means when we use a sample size that's a little bit smaller and a sample size that's maybe a little bit bigger. So, I'm going to change, in this version of the applet, I'm going to change my sample size to something as low as 2. So that means every time a sample mean gets plotted, it's only based upon drawing 2 marbles with replacement. Whereas this one down here is going to be a sample of size 25. So you're drawing 25 marbles with replacement and then taking the average of those 25 marbles. So I'd like you to see this. If we click on 10,000 samples, the picture on the bottom is much closer to a normal distribution than the picture in the middle. And so this speaks to the fact that if we want to see that true normal distribution arise, then sample size is actually going to be significant. In fact, there's something known as the central limit theorem. Write this down. And the central limit theorem is one of the biggest ideas in all of statistics. And the central limit theorem states the following. It states that the sampling distribution of sample means, I'm going to write this down, the distribution of sample means is approximately normal for a large sample, and we're going to say a large sample is when n is greater than 30. So even here in this applet, when n equals 25 on the bottom, that's still not quite the number that we need according to the central limit theorem, but it's very close. And that distribution at the bottom of that applet is in many cases we would work with that just as the same way we would with a sample of size 30. And in a lot of cases, even samples of size 10 and 15 might produce distributions of sample means that are relatively normal, even much better than what we had in the middle. And a lot of that does depend on what the original distribution of the population is. But the most important part of this central limit theorem is not even something that I have down here yet. See, the central limit theorem says the distribution of sample means is approximately normal for a large sample, at least sample size greater than 30, but that is from absolutely any original population, from any distribution. And so we can illustrate this in the applet. I'm going to reset the applet and I'm going to change my original population to a skewed population. And once again, we can play around with the sample size. If we want to leave it at n equals 2, n equals 25. For consistency, we can do that. And let's do 10,000 samples. And once again, you know, this has some normal-like properties in the middle. You're much closer to that bell curve pattern on the very bottom. Remember, because your n is getting much closer to that number from the central limit theorem of 30. N equals 25 seems to be pretty good here for getting our distribution of sample means approximately normal. But again, according to that central limit theorem, we need that little bit bigger of a sample size to truly state that this distribution would be approximately normal. But the idea is, again, we started with a distribution that, you know, previously was uniform, now it's skewed, and if your sample size is large enough, that distribution of sample means itself can just be a normal distribution. You can also look at this where the original population itself is normal. And if the original population itself is normal, we simulate this. We see that both of these have pretty good characteristics of a normal distribution, and in particular that bottom distribution is, again, it's going to be a little bit better because that sample size is close to that magic number of 30. It definitely helps that the original population itself was normal, and so in that case your distribution of sample means for many sample sizes it's going to look approximately normal. But the rule that we're going to stick by in this course is whenever we're working with a distribution of sample means, or whenever we're hoping to work with a distribution of sample means, we're going to ensure that our sample size is going to be at least 30. And then when we have that distribution, and by the way, we're always going to label that the X-bar distribution, it has these characteristics where the mean of the distribution of sample means is the mean of the population, and the standard deviation in the distribution of sample means is the standard deviation of the population divided by the square root of the sample size. So this is a little bit of theory, but it sets the stage for doing some examples that we'll be solving in the next video.